Welcome. My name's Bree, and I'm just going to take a moment to introduce our guest speaker, Dr. Russ Congalton, who we're very lucky to have with us today. He has spent a substantial amount of time being a professor of remote sensing at the University of New Hampshire, located in Durham. And he's taught classes, including the science of where, remote sensing, photogrammetry and image interpretation, digital imaging processing, and geographic information systems. So, what we have on our hands today is a geographic information science expert. So, we're really excited about that. Not only is he an expert, he was also the principal investigator of remote sensing and land cover with our very program, GLOBE, which stands for Global Learning and Observations to Benefit the Environment. And that was kind of in the early stages of GLOBE in from the middle of the 1990s into the mid 2000s. He also has many credentials and has published many papers and chapters. And I just want to say thank you for this presentation today, Russ, and I'll hand it over to you to get started talking about land cover through time.
Great. Thanks, Bree, and thanks to Globe for inviting me, and thanks everybody who's joined us live and anybody who listens later on. So I retired back in January, and I knew I was going to retire, and so I've spent since last summer till actually still doing it a little bit, cleaning out my lab and cleaning out my office and going through all kinds of things. And so I found so much of the Globe materials that we had developed and so many souvenirs of Globe and all kinds of great memories. And so when I was asked to do a presentation, I thought it would be great to do a little retrospective. And I definitely loved my time with Globe. It was very special and a lot of hard work. And what I want to do today is just kind of share a bunch of things that we developed and worked on and had a great time with. And I also need to acknowledge that I'm now very active in what's a consortium in the US called America View. And if you like the resources of Globe and you want to look and see for more educational and science, remote sensing, GIS kinds of resources, I suggest you go to the americaview.org website and you'll find more things there. And it's because of my Globe experience that I was able to kind of jump right into um, being part of America View. So we'll jump in here and look at a little retrospective. I guess I call it a walk down memory lane, as you will. So, all right. So we're not moving. There we go. All right. So a little bit about the team. There were a bunch of people at the University of New Hampshire that proposed in Globe. And in fact, Dr. Barry Rock was the first chief scientist. And Barry was at the University of New Hampshire and brought to our attention this opportunity. And so there's no pictures of Barry in this presentation, unfortunately, but we definitely owe a lot to him. Uh, have a bunch of different people who worked with us. Gary and Dave Bartlett in this first picture. I don't know if you can see my mouse or not, but Dave was the PI of the carbon part of the team. And then we have a bunch of people in the middle here. Larry and Gary were our head trainers. A lot of you probably recognize Jen Bourgeau, who's the U.S. country coordinator still, and I think maybe even the North America country coordinator now. And I actually hired Jen. She was a teacher, and we wanted to have somebody who actually was a real teacher, a K through 12 teacher, and we hired her, and we worked with her for 10 years. And then a bunch of different graduate students and different people that I'll introduce you to as we go. We were able to produce a whole bunch of different literature out of the 10 year, 12 years we had with Globe. We did 2 peer-reviewed journal articles, a book chapter. We had papers published in scientific conference proceedings, but a lot of graduate students work on this as well as undergraduate students. And then Globe has an annual conference that we were able to do proceedings from. So So what I want to talk about today is land cover and kind of show you what we did and why we did it and why it's important. And so hopefully you know a little bit about land cover, but you know it's impossible for us to go to every place in the field to visit everywhere. And but we want to monitor the Earth as often as we can. And so the way to do that is through remote sensing. And so having imagery available to us is really, really important. And these days has become absolutely amazing. And so we can make maps from that remotely sensed imagery, and we can make maps every year or every month or every week or whatever we need to, and we can look at how things change. And the big question, and what my research over the last 45 years has been, is what's the accuracy of those maps? How good are they? Can we do a really good job from this remotely sensed imagery? And so my master's thesis, my PhD dissertation, and probably half of the 115 or so papers I published and books that I've written are on this validation, this how to decide how good your map is that you made from remotely sensed data. And in order to do that, you're not going to go visit every place on the ground, but you do need some information about the ground to compare to the map. You need it in actually two places. First, you need it to help train so you can actually either train the computer or the human being who's going to interpret the imagery. And then you need an independent data set later on in order to do a validation. And you'll see as we go through this process how that all works. And so it made sense that we could have citizen science or GLOBE students learn about remote sensing, learn about the imagery, but also to collect information on the ground. And that's really what this whole land cover component of GLOBE was all about. And so what you would do is you would select a study area. Typically that was around a school. You would acquire the remotely sensed imagery. And back then, imagery wasn't free. So these days, Landsat and Sentinel imagery is free. USGS made Landsat imagery free, thank goodness, in 2008. But that was long after we had started on this project. And so actually, if a school started to do land cover mapping, they got imagery, Landsat imagery sent to them from the Aros Center in Sioux Falls, South Dakota, which was a nice being able to do. Okay. Then you have to decide on a classification scheme. What are the important information that you want to get from the remote sensing? Then you actually create that map. And as I said, it requires some ground data, not 100%, not going everywhere, but some samples, some representative samples of what's going on. And then later on, you want to do that accuracy assessment. You want to validate, you want to see how good the map is. And for that, you need an independent sample of ground data. You can't use the same data that you trained on. You need an independent sample. Okay. So we built a bunch of land cover protocols, and the protocols are science. The goal here was to maintain the same scientific integrity as a regular land cover or remote sensing scientist would do, with the goal being that if the students had great training, they could collect data that could be used by the scientific community as well as by the students themselves. And so there's the land cover sample site protocol. And this is for going to the ground and collecting some data on the ground for a land cover area. Sometimes measurements were required, depending on what kind of land area you were looking at. If it was water, there's a whole set of GLOBE protocols for water quality and water measurements and things like that. But for this, we only needed to know it was water. But if you were in the forest or some other vegetated areas, there was some information that you could measure. So biometry is life measurements or biometrics, if you will. And so there were protocols set up for that. And then there was protocols for either doing a manual or human being interpreted land cover map, or if you were going to use the computer for doing that. You have to remember that in 1995, the computers were pretty rudimentary, only, not that sophisticated. And in fact, your cell phone right now is much more sophisticated than any computer we used in 1995. So there were some limits there. And then lastly, we developed a change protocol so you could look at land cover change over time if you were so invested that you were doing this year after year with your school. So these are the protocols. But in order to justify the protocols and to get the students knowledgeable about what was going on, we built a series of learning activities. And the learning activities were meant to introduce the students and the teachers and whoever else wanted to learn about this to these different scientific concepts. So we had something called Odyssey of the Eyes, which kind of introduced the concept of remote sensing. We did this really cool activity with called Digital Faces, where we helped people understand the concept of pixels. These days, everybody understands a pixel because of the quality of your television or the camera on your phone, but in 2000, nobody, 1995, not at all. So we had to get this idea of these little squares, these little cookie cutters, and how that represented what people were seeing. And so they would actually transfer verbally information back and forth to each other and try to transfer a picture from one person to another person. Kind of interesting stuff. And then we wanted to get students involved in the idea of classification, which is a key scientific term. And so we talked about classifying of leaves. Then we talked about a classification system. So we needed a worldwide classification system, and I'll talk more about this shortly. But we came up with a dichotomous key. Becky Bozier, who's part of the Globe Implementation Office these days, was part of our team for building what we call the MUC field guide or the MUC classification. And you'll see in a minute that it's just a modification of the UNESCO classification scheme. And then we did have measurements that we needed, measurements of like canopy cover. So how dense are the trees out there? And so there was a sampling protocol and activity for that. There were some skills that students had to get. So we had to make sure there was a learning activity related to learning how to use a compass and how to figure out your pace so that you could measure distances pretty well. Again, there was the actual field measurements with the canopy cover. And then there was this idea of error and accuracy and validation. And we had two different learning activities, one at a fairly simple level for the younger students using birds. And we had different beak types, and they could classify things based on color and beak type and that kind of thing. And then we had a more advanced technique or learning activity that we used with different kinds of clouds, which worked out really well for GLOBE because GLOBE already had a cloud protocol as part of their atmospheric component of GLOBE. So a little bit more detail on land cover mapping. So again, we first you select the study area. And for GLOBE, this was a 15 kilometer by 15 kilometer area that was centered right around your school. So the goal was to be able to walk to places on your, right off school grounds or even your school parking lot or something like that. But hopefully there was some playgrounds and maybe some woods in the area, depending on where your school was. And 15 kilometers by 15 kilometers, that's not a whole Landsat scene. It's a small piece of it, but it worked out fairly well. And then, as I said, Eros would send the school on a floppy disk, actually a little 3.25 floppy disk. So in the old days, that's how data was distributed. And a little 15 by 15 kilometer piece of Landsat imagery fit on a floppy. So that worked out okay. And so that was nice that the school got that. And I threw out hundreds of floppy disks when I was cleaning out my lab over the last 6 months. And then, as I said, we came up with a classification scheme. It was absolutely key that the scheme was universal, that it would work for anywhere in the entire world, so that and everybody said forest, we all knew what a forest was. Or if everybody said pasture, we knew what a pasture was. Okay, so we took the UNESCO scheme, which actually initially had 8 natural land cover classes, and we added the two developed classes to it. So we came up with 10 level 1 classes, 10 very general classes. And then it's one of the nice things about a classification scheme is that it could be hierarchical. And hierarchical means that it goes from very general classes to very specific classes. For instance, you could think of forest, okay? And then when you have forest, you could have level 2 could be like evergreen forest versus deciduous forest. And then you could break the deciduous forest down into oaks and then maples and birches and, individual trees. But then you could take the birches and break it down into, white birch and paper birch. And so you can get different levels. It gets more and more detailed as you get further down the hierarchy. And so the way the Muck scheme came out, we have 10 level 1 classes, but there's 164 level 4 classes. We actually spent almost 2 years testing out this scheme, developing it, making it into what we call a dichotomous key. A dichotomous key is absolutely so important to this because it makes it easy for you to do. It asks a question. It says, is it this or that? And if it's yes, you go to one place. If it's no, you go to the other place. Okay. So if it's natural vegetation, then you would go to one of the 8 classes for natural vegetation. If it was developed, you would go to one of the 2 places for developed. So it's a partitioning, a binary partitioning, a breaking into yes or no, this choice or that choice. The key is 164 pages long, so it takes a while to get through it if you want to go all the way down to level 4, but it's really, really important. And the amazing thing about it is that it meets all the class requirements of a good classification scheme. It's not just forest, but it actually defines what a forest is. It's not just shrub, but it defines what a forest is. I've already shown you that it's hierarchical. It also needs to be mutually exclusive and totally exhaustive. Totally exhaustive means it covers everywhere in the whole world. And if you're standing someplace, you're going to be able to come up with one of those 164 classes. And mutually exclusive means that there's no confusion between them. And that's what was really nice about the dichotomous key. So here's an example. Some of you are watching this probably know all about this already because you've used the Muck field guide, or now it's online, so you can do it online, or it's part of the app, so you can do it on the app, and it works out really well. So here are the 10 level 1 classes, and you can see that there are definitions. And so, for instance, a forest has to be at least 40% of the area has to be trees. This is where some measurements would come in. And the trees have to be at least 5 meters tall. If it's not 5 meters tall, then it's not a forest yet. Okay. And so, again, important to have these definitions so that there's no confusion between what's going on. And here you can see the hierarchy. So closed forest, and then you break it down into mainly evergreen closed forest, or mainly deciduous closed forest, or extremely xeromorphic or dry closed forest. So you can see we take the 0 from closed forest, and then there are 3 level 2 categories, and then we can continue to break that down to 4 levels in the hierarchy. It gets pretty intense. And so here you can see here's herbaceous, barren, wetland, and open water. And then we get down to cultivated and urban land, which are the 2 categories that we added to the original UNESCO system. And so we called it MUCK, the modified UNESCO classification system. So if you get into this, you can muck around if you want to. So. And then we provided all kinds of cartoons in the field guides and in the GLOBE user's guide, so students could practice, they could see what was going on. And so here you can see about 80% of the site is covered by graminoid and forb with about 1 meter tall. And then there's 75% graminoid, 25% forb. There's some broadleafed deciduous trees, but only 15 to 20%. Okay, what does that mean? And so then students could go through the Muck field guide ask the questions, go to the right place in the area and answer the answer. This is the thing. And the cool thing about that is that students got really into that. And I love this. Some students actually, and the teacher, sent us this slide one time. So what's going on there? Well, the, the donkey or horse or whatever that is saying, of course, it's Muck 813. Otherwise, I'd be out there. And Muck code 813 is confined livestock feeding. So the animal is correct. It knows it's stuck in the pen. So um, students were able to pick up on this. It was really pretty straightforward, and the guide kind of leads you to that. So very, very important to have this classification scheme so that everybody spoke the same language, no matter where we were on the planet, and really cool. Okay, so what do we do next? Well, then we want to start thinking about the process of creating a map. So if we're going to create a map, we need to go to the ground. Okay, so when you go to the ground, you find what we call land cover sample site. And that land cover sample site, it needs to be homogeneous, and it needed to be about 90 meters by 90 meters in size. So you would find an area, say a forest that was all forest, and you would go into the center of it. And in the center, you would kind of put a stake in, and then you would make sure you had something that was about 90 meters by 90 meters in size. Why 90 meters and 90 meters in size? Well, it has to do with positional accuracy. So we're going to talk about how good the map is, which is thematic accuracy. But positional accuracy has to do with, are you in the right place? And if you're not in the right place, then it doesn't matter that you got the label, the map class correct if you don't know where you are. And back then, GPS was pretty new. It was not super accurate. It was expensive. It wasn't on your phone yet because there were no cell phones yet in 1995. And so we wanted to make sure that you were in that area. And therefore, even if you were off by a little bit positionally, you were still inside of that single area that was all one land cover. Okay, so homogeneous land cover was really, really important. We asked the students in the class to do at least one land cover type per study area. And there were observations they made there were obviously the location. Then they had to figure out the muck code, and then they would take photographs in the 4 cardinal directions and then straight up and straight down. So we would have a record, and we could visually do a little quality control of what they said the muck code was. So again, as I said, GPS was kind of new at this point, and most schools didn't have a GPS unit. And so at least in the US, I know a Globe US office actually shipped GPS units to schools. So schools would borrow them. And then some schools could afford to buy some, and then they would share them around in their state or in their region or whatever. And there was a protocol, scientific protocol for using the GPS, and there was a field form to fill out, and you had to record the GPS coordinate once per minute for 5 minutes and then average that. That actually improved your positional accuracy. You needed to report out to the 4th decimal place in decimal degrees. And there was also an offset protocol. For instance, if you were on the edge of water, we didn't expect you to go into the middle of the lake and get a GPS location. There was a way of knowing what direction the water was from you and getting the exact GPS location towards the center of the lake without actually having to swim for it. So that was important. Okay, and as I said, other measurements might be needed. So things like the canopy. You might remember that the canopy there had to be at least 40% trees. There had to be some density or canopy closure measure. And so we actually designed this instrument called the densiometer. What we did is we used a toilet paper tube, or if you really were in there, then you bought a little PVC pipe tubing that you could use. And all you really needed was floss, a toilet paper tube, some tape, and a nut. And you can see that you could put these things together and you would basically hold the instrument in your hand, look straight up. And from the diagram here, if you could see that if the crosshairs had vegetation in it, you counted that as vegetation. And if the crosshairs didn't have the vegetation in it, you didn't. Okay, so you were able to make some measurements. Now, measurements weren't necessary at every muck site, but if it was forest, canopy was important. So in addition to canopy, height was a deal. I remember I said that in order for it to be a forest, it had to be 5 meters tall. So you can use something called a clinometer. A clinometer you actually can build, and a clinometer allows you to measure height. And so we had a handout. All you needed was a piece of cardboard, a string, a straw, and a little weight that you could use here. Well, most people use some kind of piece of metal, and you could get a clinometer. And then you got to do some math, which was kind of a cool thing to calculate the height. This is the same kinds of techniques that foresters use every day to measure the heights of objects. And so we were bringing the scientific protocols down for all GLOBE students to use. Okay. Then you could either do manual mapping or computer-aided mapping, depending on kind of what grade you were in. So manual mapping meant interpreting the imagery by looking at it, and computer-aided mapping meant using some software, some really cool software out of Purdue University called Multispec, which is still freely available and anybody can use and download. Just go to Multispec Purdue University and it's right there for you to use. And so here's an example of a Washington, D.C. satellite image. And here's a school that did the muck codes and classified the area manually. Or you could do the same thing. This is a place in the Ukraine, and you could do it using the multi-spec computer processing, image processing analysis. So once you had that, then you want to know, how good is it? Did I do a good job? Okay, so you need some independent ground samples in order to do that. So we want to compare what the map says to what it really is on the ground. This is done using what's called an error matrix. And what the error matrix does is allows us to study those patterns of error to see if we're making a systematic mistake. Is there just something we didn't train quite right? What's going on with that? And so this was actually straight out of the muck the GLOBE manual on what's going on here. So you can see we've got an area that we've mapped. We've got different land cover. And you can see that what we've done is for different study area, different sites that we've gone to, we've got what the map said the muck code is and what the ground said the muck code is. And we would do a comparison. So for instance, in Town Reserve, the map said it was 4110, but when we went there and visited it on the ground, it was actually 1121 muck code. And so that's not correct. Versus Brown's Woods, you can see 0222, and that's true for both of them. And so that was correct. And so here's at the bottom is the error matrix. And you basically, it's a contingency table or a cross classification. On one axis is what the validation data says. On the other is what the map says is going on. If you get it right, you tally in the major diagonal. If you get it wrong, you tally in the place to show what's wrong. So for instance, here, it's the validation data said it was 1121, but the student's map said it was 0222. Okay, so you just tally. And then eventually you add it all together. You get an error matrix that looks something like this, where you have enough samples where you can actually get some statistical validity. The cool thing about this is, schools might be able to put their maps together. Certainly scientists would love to have the students' data so that they could use that data in conjunction with projects they're working on. And I'll show you some of the projects we did where we used student data to test to see if they were doing a good job. And so here's a typical error matrix. Again, we could be able to calculate the overall accuracy of the map by summing the major diagonal and dividing by the total. And we can calculate things called producers and users accuracies as well. So, so probably most importantly here, how does all this fit into the classroom? That's what we were trying to do. We were trying to get the, the teachers and the students excited about using remote sensing, about going outside and collecting land cover data. So you can see from a land cover mapping standpoint, we could do something about the history of your local area. So from a social studies standpoint, we could look at change detection and development, environmental awareness kind of issues. So from other science classes, maybe environmental science class, community involvement is important. The idea of classification is a key scientific concept, and so students could get a good grip on that. This ability to do manual interpretation, students could look at similarities, different kinds of patterns, colors, understand the remote sensing. If we got into the satellite imagery and actually did the processing, obviously that's all a bunch of numbers. The data collection for validation, all the measurements that have to be made, the tree height, that involves geometry, trigonometry, averages, angles. We have pacing, we have compass work, again, from a classification standpoint, tree ID, maybe even ecosystems. You can get into it from a completely non-scientific area and think about from an art, what they want to do from drawings and sketches and maybe even photos that they take, and even from a language arts standpoint, writing and describing what was going on. So all kinds of opportunities for using this in the classroom. And then from an accuracy standpoint, that's important that students understand the scientific process and how scientists prove how they're correct and how they're not correct and what mistakes they made, and a whole discussion about that. And then obviously these days, there's all kinds of possibilities with GIS. We didn't really have GIS capabilities, very much software back then, but these days GIS software is more readily available. And then Earth as a system, and eventually, the kind of the fifth component of GLOBE was to put all the different GLOBE protocols, the atmosphere and the soils and the water hydrology and the land cover together and look at the Earth as a system. And so that became incredibly important. So what I want to do now is show you that we actually did this. The goal for our team was, can it be done? And so I'm going to look at just the muckathon concept and then show you quickly a few different examples of where we did this. And I can't go into gory detail, but there are publications written about most of these things, at least master's theses, if not. And if anybody wants to contact me, I'm happy to share anything with you that I have. And I know that Amy Chen has collected a lot of this information, and I think the GLOBE office probably has it as well. So, but feel free to contact me if I can help you. So the idea of a muckathon was to get as much land cover sample site data as possible in some kind of concerted effort. And so we implemented that in a bunch of different ways. And so really, really important for the students to be able to understand the imagery and collecting the ground data and how those two things related. And obviously you need a whole bunch of land cover samples to be able to assess the accuracy of your map. And probably the most important and greatest thing beyond what the students were doing is that real scientists would use this real data that the students were collecting. And so it wasn't that they were just doing a project for themselves. It was great that they were doing that for themselves and learning, but to know that that data could be used by lots of other people is pretty cool. So our first big pilot study was in Pawtuckaway State Park, which is in New Hampshire. We had 15 trained teachers and about 527 students. Some of them were actually campers. So there was a summer program at the state park. They did a bunch of learning activities, which they were completed at the schools, and we evaluated that. You'll see some evaluation at the end. They collected the land cover data, and we evaluated how they did that. And then we did a bunch of data analysis and actually created some maps at the end. So um, it was divided into different groups. So we had first through fourth grade as class one, fifth through eighth grade as class two, and ninth through 12th grade as class three. And so you can see on this map the different areas that the different classes worked on. These are all forested areas in Pawtuckaway State Park, about 25 minutes from the UNH campus. So this is one of our master students, Alan Freed, training the teachers in old lab, long time ago. Um, Here's another master student, Becky, who was also part of that. So the two of them actually did their master's theses on this. And then we had teachers go outside and practice. This is on the Durham campus. But then we had the kids all go out and they did it. So you can see we're doing a little compass work here and they're still smiling. So we're doing okay. No, that kid is not stuck on that post there, even though it looks like he's impaled. While he was standing right next to it. That was the center point, marking what was going on. Here's them using the canopy cover tool, the densiometer, and you can see it can be a little tricky. It looks like our one guy there is eating the washer or the bolt that's holding that up, and obviously not quite straight at this point. But we had to work on that. That's why we had to have some training and make sure there was some adult supervision to help them out, but they got it eventually. And again, you can see that that's not a toilet paper tube that one on that one. So they must have done some PVC pipe, which was great, tallying the field data and still smiling. So what we did is we did some really detailed analysis here, by different age groups, and we had them do some different evaluations. And again, we had globe schools, we had some non-globe schools, which were and then we had the campers. And so we have some observations here. And again, I'm just going to go through this quickly. But as you might expect, the younger kids needed a little bit more time on the learning activities. So on average, about 5.7 hours. And the older kids, the high school students, not so long. Okay? And then we asked some different questions. And this is just a graph of 345 respondents. Not everybody responded, but what percent they got correct. So we asked, what's a classification scheme? We asked things like, what does a remote sensor see? You can see they had some trouble with why did they need to know their pace, but they did great with measuring canopy cover. They understood what that was about, and they seemed to have a good feel for what MUC, the classification scheme, was. So again, pretty decent results. We also asked them to comment on their field work, because obviously they practiced in the classroom and then, outside, where there wasn't any mosquitoes, where there wasn't any boulders, where there wasn't any hills, where there wasn't any limbs and branches and tree trunks they had to step over. And so you can see the things that they kind of commented on about. They didn't like bugs. Don't blame them. They thought pacing was a little challenging. They weren't so happy about the dense underbrush. Some of the tools were hard to find, these kinds of things. So not everybody responded, but we got feedback so we could continue to improve the protocols and make sure that the learning activities were such that they were getting the right concepts down. So we made some observations. The younger students needed a little more guidance, especially with the compass and pacing. The middle school students exhibited the widest range of maturity and ability, but were incredibly enthusiastic. And that was probably my favorite group to work with, and historically true. And then the older students, the high school students, they got it and they worked pretty efficiently, and that was really cool. And from sixth grade on, we felt like they could work pretty independently. The camp groups had less preparation, less learning activities. They did some in the field, but not as much as the school groups did. But they were campers, and so they were less bothered by the field. They were more used to being in the field. So kind of the opposite for the school groups. And then we were able to produce a land cover map of the Pawtucket area that we then shared with the different classes. So a few conclusions that we got from the study is that the training materials were good and effective. The practical and hands-on activities were the ones that the students liked the most. We felt very good about the accuracy of the student data that was collected. They didn't have much difference between age groups once they understood what they were doing. Any classification confusion was between things that were kind of really closely related, and that classroom work, that training in the classroom really helped to improve the field efficiency. So that was great. So we moved on. We did another pilot kind of study with Dutchess County, New York. So there was a bunch of schools there that were interested. There was a learning center there. And so we were able to produce, again, a land cover map of the whole county, so much bigger than Pawtucket State Park. We did a lot of work with this. Here's a terrible photograph of the participants that worked on the muckathon. You can see that we had a number of really active teachers there that really helped with this. We produced a bunch of imagery that they could then take to the field and use as part of their ground collection activities, which they were very excited about. And we actually assessed the accuracy of the map that was made from the data that they created. And we got about an 80% overall accuracy, which is very reasonable. Very happy with that. And we determined that the land cover biology team was successful in using that student collected data. The GLOBE data was extremely valuable in that it allowed us to augment the information that we already had. Because of that, we were able to do a larger area, and obviously the students benefited greatly by doing real science and getting excited that this was useful, that the information that they were gathering was going to be used in real research. This is a fun one, the Maine Muckathon. We had 300 students in Androscoggin County, which is sort of in lower southern central Maine. The goal here was to create a land cover map and do some change detection. So we're going to do 1993 and 2000. The GLOBE data was going to be used for ground collection to perform a supervised classification, which using the multi-spec software. And then we were going to do change detection analysis. So this was 2 master's thesis, student theses. And we actually were able to do that. And so you can see the 2 maps here. But there were some lessons learned. We had an amazing Muckathon day. It was a Saturday. The teachers had done all their training and the learning activities. The parents and the teachers showed up and were super encouraged. Had busloads of kids showing up. Dunkin' Donuts actually came out and provided donuts and hot chocolate and coffee for the parents. The students were incredibly enthusiastic. And then one of the teachers decided that they knew a little bit more about GPS than we did. And they told all the students to truncate the GPS data and not keep all the significant digits, making the data completely useless, which was such a disappointment to us. Instead of being plus or minus about 10 meters positional accuracy, we were now plus or minus about 1,000 meters, which completely ruined all the data. So we learned a strong lesson that we had to make sure that the teachers understood the science behind what was going on and not try to make it easier for the kids by not keeping the significant digits. So that was a little scary to us. Want you to also know we did a project in New Zealand, sent a graduate student down to New Zealand for half a year. We had partners with the University of Waikato down there and a private research institute, as well as GLOBE New Zealand. And the students spent a whole bunch of time. Actually, my co-PI, Mimi Becker, and myself spent 3 weeks down there, initially setting things up and then letting Jesse spend 6 months down there doing some pretty cool mapping that we shared with the different cooperators with the university and with the Landcare Research Institute, and worked out pretty excited. That was great. Um, Globe One. Globe One was this really cool project that happened, kind of a grassroots effort out of Iowa with an amazing group of scientists that wanted to do this, and a fantastic state coordinator in Iowa named Marcy Seavey. And I'll show you Marcy's picture. And actually, she was in the part of our team picture at the beginning. But they were really interested in doing some joint research and supporting what GLOBE had going on. So it was basically a field campaign, K through 12 students working with scientists and their local community. It was for a full year, spring of 2004 and fall of 2005. It was in Black Hawk County as part of University of Northern Iowa research. And there were tons of students that participated. It was amazing. And what they wanted to do is they wanted to look at how land cover affects their local soil, atmosphere, water, and plants. And in Black Hawk County, land cover really means agriculture, mostly corn and soybeans. They wanted to look at soil tillage techniques and what happened if you did some crop residue retention at the end of the harvest. And they also were interested in prairies and urban areas. So here's the map of, or the imagery of the Black Hawk County, and where those pins are where a bunch of study sites were set up. And here's the team at work. So some of you might recognize Jen there with her hair nice and short, talking about what a muckathon is. And here we're dealing with lots and lots of teachers who were very happy to participate and wanted to work on this. So that was a great project. Quickly here, I want to just talk about two more projects. Croatia. Got to go to Croatia, which was amazingly cool. So you can see this was in 1999. The first time I visited, the first day I spent on it was a high school at sea. So it was a boat, which was kind of fun. I got on the boat and I had my globe hat on, and the captain took my globe hat and gave me his captain hat. So I ended up with a high school captain hat after that. In the picture over here, you can see Dixon Butler. So some of you may know Dixon was the second chief scientist, but the chief scientist through my whole time at GLOBE. Barry got things going and stepped down, and then Dixon was amazing and really did a great job as the chief scientist. And then the second day of this trip, I did training for teachers. So we had a bunch of teachers come into another high school area, and we taught them especially about multispec. They were really interested in learning how to do the digital image classification. Really wanted to share this one with you. This is the second time I got to go to Croatia, and Croatia's a beautiful country. I really loved it. But we had this student learning exhibition, or expedition, I guess is the right word, in a national park and then on an island off the coast in the middle of the Adriatic, which was fantastic. And you can see here what was set up is a bunch of different sites. So the students can go from place to place to place and practice their land cover mapping. This down here is Marcy Seavey. So even though she did Globe One, she also came to Croatia, and she's holding the muck field guide. But what I thought was absolutely phenomenally amazing is in order to get out to the island and to come back from the island, the Croatian Navy sent this amphibious lander, which came right up to the edge of the beach and put down that whole opening door. And the students just walked onto this big hole in the ship, which it was probably, I don't know, it was easily over 100 degrees in there. They'd been working all day long in the field doing amazing stuff. And they just sat down and they started to just sing different songs and entertain each other and had a great time. And they could care less about it. It was just absolutely phenomenal experience. So I really enjoyed both my trips to Croatia. So just to summarize, my time at GLOBE was an amazing experience. We worked really, really hard. Our whole team worked incredibly hard to make sure we could prove that there was scientific and educational value of the learning activities and the protocols that we developed. And those were tested and tested and tested and revised. We had 2 full GLOBE manuals that came out during our tenure there. Um, Unfortunately, I would say that a lot of what we did was a little bit ahead of its time. Remote sensing was kind of new. I would say remote sensing became ubiquitous around after 9/11, after the World Trade Center was hit by the airplanes, and all of a sudden the world got to see imagery after imagery. And these days, you see imagery, satellite imagery, or aerial photography, or other kinds of space imagery of every disaster imaginable, of a war in Ukraine, or tornado, or hurricane in Louisiana, or whatever. But back then it was kind of new, and the internet was new. The teachers hadn't been really exposed to the internet. A lot of the Globe teachers were just learning. They came because they were excited about learning what the internet was all about. Computers were somewhat slower than they are now, and so I feel like everything that we did is 100% valid and should be implemented. And yet at that time, it was probably just a little bit too soon for them. So I'm really glad to see that GLOBE is still in existence and that it's doing well. And I'm hoping that with some of the people that are working on the land cover work now, that we can kind of reinvigorate some of those things and get more people doing it. It's eminently doable. And I think with the technology that we have these days, it's fantastic. So definitely was very proud to be part of GLOBE, and really happy to be able to kind of share my time down memory lane with you today. So thanks a lot for your attention. And I don't know if we do questions or not, but I'm happy to do whatever Bree tells me to do. So
Yeah, absolutely. Thank you for that presentation, Russ. That was lovely and very insightful. Yeah, I'd like to open the floor to anyone that has a question. We have about 5 minutes or so, but if there's a flood of questions, we'll see what we could do. Go ahead and raise your hand and unmute yourself if you have a question, or if you're more comfortable, you can put it in the chat and I'll ask it for you.
All I have to say is that it was really awesome. And this is Peggy Folletta from California.
Hi, Peggy.
Yeah, hi. Russ, I met Russ's daughter at Elkhorn Slough when he came to visit, working there now. Anyway, it was a great introduction to GIS for us. It was one of our favorite protocols or protocol areas through the years to look at the land cover. I mean, that's what it's all about. The data is on land. It was very exciting, still is. So thanks so much, Russ, for all you've done through the many, many years.
Thanks. I'm so glad to see you. I was just out in California last week with Emma, and it was so cool. Peggy was one of the superstar teachers of GLOBE for sure in the U.S., and I hadn't seen her in forever. And we went to Elkhorn Slough, which is an area near Monterey, California. My daughter works at the Monterey Bay Aquarium, and Peggy actually is a volunteer at the Monterey Bay Aquarium, but she also works a volunteer at Elkhorn Slough. And I was standing there at the gift shop, and in walks Peggy. And of course, Emma, my daughter, knew her. And I was like, she comes up and starts giving me a hug. And of course, I didn't recognize her. So she's like, I'm Peggy Folletta. I'm like, oh, of course you are. It was awesome. So thanks for sharing, Peggy.
Well, I didn't connect the Congalton and Emma to you until I saw you standing side by side. And my jaw just dropped. And I just said, I said, I know you.
That's it. Well, she's much smarter than me and is doing great stuff. So thanks.
Hey, Russ, this is Becky.
Hey, Becky.
Yeah, it's great to see you again.
Yeah, you too.
Yeah, it was 1998 when I started as a Knaus Fellow and was introduced to the land cover in Dixon put me on to work with you. And I think we met at Snowmass in person. I think that was the first time. And, oh, you just brought back so many memories. And at the time, I was a graduate student and using GIS and this whole idea of citizen science, and that was all new to me. And you were very transformational in my thinking and what I did for the rest of my working career. And I still continue with GLOBE, and a large part is due to your influence and your team. So thank you.
Oh, sure. It was excellent to work with you. And as I said in the presentation, Becky was one that was instrumental in getting the Muckathon Muck book done, the field guide. And Jen took all 50 of my printed copies that I had left, Becky. So you have to ask Jen for them. I saw Jen's on here
I
someplace.
think I have a couple, so I'm holding on to them tightly.
I actually have one, so I had to still, but I didn't want to keep too many of them. And Jen, that she eyeballed those the most when I laid out a whole table's worth of stuff that I have. So good to see you. Thanks.
Well, I have a question. If it's 10 o'clock, do you have time to answer a question or two?
I do. Yeah, I can stay on as long as people want to stay on. So
Okay, great. So, yeah, I think it was really helpful for me as someone who's new to working with GLOBE to kind of see the history of how some of like these processes and protocols evolved, and think about that. So I guess one question I have is, basically the muck protocols do an awesome amount of work to get people taking the data on the same page, and globally even. But how can is there a way that might make it easier for like scientists in other disciplines, or like in that are kind of ecosystem focused, but still are kind of collecting similar data, but maybe don't always use the same phrases, to like make this classification system a little bit more approachable for people that are used to different vocabularies?
So that's a great question. I mean, I think there is always jargon in science that, everybody has to kind of come together and figure out and maybe simplify. The cool thing is we used the UNESCO scheme, which was a worldwide scheme. So most of that terminology was theirs, not ours. And so scientists from all over the world came together to come up with that. So it's pretty universally accepted. I would expect most ecologists, would not be bothered by that language. Some of the stuff, sounds really scientific where, you could use the word dry instead of xeromorphic, but of course we put dry in parentheses so people would understand. And so I think the guide itself actually has a bunch of terminology explained in it, and it has like an intro 8-page introduction that kind of gives the philosophy behind that. So I mean, if you make it so that it's not clear, or if it's ambiguous, then the data suffers because everybody thinks they know what a forest is, right? But you have to have EPA has one definition of forest, and Forest Service has a completely different definition of forest,
Yeah.
because the Forest Service wants everything to be called a forest so that they can manage it. And so maybe there only has to be 25% of the ground area covered by trees for the Forest Service to call it forest. But, EPA might call forest, it has to be 50% trees. So if we just say forest and we all go out there, we're going to have lots of different things called forest that one person thinks isn't a forest and the other person's like, it's definitely a forest. Whereas if you've got, and it's really cool that the guide is a dichotomous key because
Yeah.
it just goes step by step by step. And you don't have to go to level 4. I
Yeah.
mean, you could see on a lot of our projects, we went to level 1 and some, level 2 and others. Sometimes we went a little further depending. But and the nice thing is, even though there's 164 level 4 classes, your area is not going to have all 164 in there, right?
Right.
Unless you're mapping the whole world, which, you know, we would need a lot more money than Globe has to do that. So
Yeah. So
yeah,
what I'm hearing you say is kind of diving into the details of the classification guide that was put together and like looking at the numbers and kind of understanding the information is there in a detailed enough way for other people to translate it to some of what they also understand in different terms.
yep, yep.
Cool.
Yeah, and the kids got into it. They loved learning these different words for things. They would thought they were cool, and it's zeromorphic now, And so it was really interesting to us that it was frankly, Globe didn't bother the kids. It was the teachers that had a harder time, mostly in the U.S.
Mm-hmm.
Internationally, I don't think that's true. There were so many schools and countries that adopted Globe internationally, but in the U.S. our attention span's not very long, unfortunately, and we get excited about this, and then we get excited about the next thing another year, and then another thing the next year, and that was hard. It was hard to keep teachers. Yeah, I mean, for years I've been trying to get back into schools here in New Hampshire. And I'll come to your school and I'll do something for you. Oh yeah, yeah, fine, fine. Just let me know. Oh no, never. This year next week I'm going to a local school, and in May I'm going to a local school again to talk about remote sensing and mostly drones, UAS things. So
Wow. Well,
have
that
a
should be so fun. And
yeah,
another thing I wanted to kind of point out with something you mentioned during your presentation was that I think when you say you were a little ahead of the times with Globe, I would have to say absolutely. Like amazing that Globe was putting together the same kind of classification and doing like the heavy lifting almost in parallel with the development of serious, not serious, but like extremely well used land cover products with Modus. Like it was almost like a parallel development. Like if you look at the history, a lot of the land cover maps that people are applying today that are usually, if it's on a global scale, or from the Modus satellite mission, which is also a NASA mission,
mhm,
was just starting up in 2001, barely.
right.
So it's very cool that you were kind of able to get these kids in at the ground level and kind of share this information actively while also like doing real science with the data that you were collecting. I really think that's pretty amazing.
Yeah, I mean, think about it today. An app on your phone and GPS on your phone solved half the problems that we had to battle through in 1995. So,
Yeah, but there is so much value in understanding how to do things on the ground. Like, even though a lot of the problems are solved, it's still connecting the ground to the
yep,
satellite imagery. So
absolutely key. Yep,
it's spot on.
yep, you're right, Bree, for sure.
Okay, let me see. I think we might have a question in the chat. Yeah, no, absolutely. Thanks for your comment, Tamsin. This was a very fun presentation, and I think that's probably a good note to end on for now. Um, thank you again, Russ.
Yeah, sure.
I think I'll be reaching out to you soon in the future, maybe to chat a little bit more about this. And thank you for sharing all of this with the Globe community.
You're welcome. Thanks for inviting me. Have a good day.
You too.
Bye bye.